So we're going to be recording this part of the session. If anybody has any objections with the recording, please say so now. Okay. And so as we were saying, Simulink is going to be this component that's a part of Matlab that's going to help us do graphical representations of models. And this is actually going to be very useful as we move on in the topics of the course, because we're going to be looking at systems kind of the way we looked at them with the azimuth antenna example. Remember that we had this very large block diagram that represented all the components of the azimuth antenna. We're actually going to be modeling that. We're going to be able to do it in Matlab with code, but we can also graphically represent the system using Simulink. And so what do we have here when we open Simulink? There's already some templates. There's already some templates here. I'm going to open a few of them just so you can see. So I'm going to open this one that says feedback controller. And so,
Professor, at least I don't see any like other window.
Oh, let me, I forgot that I need to switch over because it doesn't do this automatically. So give me a moment.
Yeah.
Just give me a moment because it literally opens up another window, and let me share that one then. Where is the Simulink window? Okay. There we go. So we should be seeing that. So that's the Simulink start page. So we click Simulink and it opens this up. And we can open any of the models here just as an example. I'm going to open this one that says feedback controller. I'm going to do a double click there. Let me just, so you should be seeing there and basically what we have here, this is a canvas. So it's very similar to Multisim, for those of you who've used Multisim. And basically what we have here is the representation of a control system. So we've got a box here that's the controller. We've got a box here that's the plant. We've got an input here, which is the reference and a comparison. We can click on any of these, and a box should open where we can define, if we click on that one, what we see is that internally it's a PID that we have there. So each of the boxes in themselves can be opened and looked at individually. Oh, close the window again. Sorry about that. And so we're going to be able to do these representation of systems. We're going to be able to do them graphically using different components that are boxes. And we're going to be able to also simulate their we're going to be able to simulate their behavior, which is also going to be practical. And so let me show you an example here where I've got an example here, which is the one we've been seeing, which is basically the transfer function. How did I define this box here with the transfer function? Well, there's a function here in Simulink that's called a transfer function. How do we get that? We go over here to the blocks or the library browser. And so we've got here the different blocks that represent different things, the commonly used. Here we've got the continuous, the category is continuous. The one we're going to be using a lot is the continuous. And here, if we click the continuous tab, there's different things that we can define here. So for example, there is one here that says transfer function. So I can bring this over to the canvas, and I can define the transfer function with the numerator and the denominator, similar to how I did it in Matlab, but I can graphically see it here as a box. Now, what do I have over here? This is just a way in which I'm going to be simulating the impulse. In the tab here, we're going to have a category for sinks and sources. So sources are going to be things that are going to provide a stimuli. There's a bunch of different things here for a source. We actually have a step function. We also have a ramp function. We've got a sine wave. There's many others here, random number, repeating sequence. There's actually not a box to represent an impulse. There's actually not a box to represent an impulse. The impulse, there's many ways in which we can create an impulse. Remembering that the impulse is going to be this very large stimuli that we're providing at a very small moment in time. So there's many ways in which we can simulate or create that. The way we're going to be doing it here is that I've got a step input that has a very large final value and has a very, 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 very small step time. So it has a very large value and a very small step time. And then I've got another one that's got a very small increment in that step time and a negative value. And so basically what I'm doing here, I said I wasn't going to draw, but I'm going to have to draw, is that I'm going to put some colors here. I'm going to say that this one is blue. And I'm going to say that this one is lighter blue. And so basically what I'm defining a signal here that's very small, a very, 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 very small step input that's very, 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 very large. And then I am defining another one that's just a little bit larger in time, but is negative. And so the end result of doing an addition, this block here does, what it does is that it receives the two signals and it's a summing point. It's going to subtract those two mathematically because one is negative, and it's going to leave me with a very short, very, 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 very short impulse that's very large. So that's one way in which I can simulate that. And I'm providing that as an input. This is the first system. This is the mass dampening. I'm sorry, this is the mass, the mass system that has the mass in the spring. And these two things that I have here are scopes. It's basically, if we go over here to the boxes and we go to sinks, these are scopes. It's like a measurement. It's like putting an oscilloscope there. And so once I do this and I run the simulation, and we can modify the simulation characteristics here if we want. We've got the simulation time here and other things. I can click on each of these. I'm going to click on here first on the scope that has to do with the step. And so this is the step. And if you notice, what I'm defining is a very, very small signal that's very large. And over here, I've got the output in the scope, and this would be the output, which is the same output that we had in the previous example that we did in Matlab. So it's exactly the same. What's the difference here? That we can create the block diagram and play around with it as a block diagram, rather than in Matlab, we're kind of working with them as objects. Let's modify this here. Let's do the other example where we had the dampening. So now the transfer function changes to this, and I'm going to run the simulation again. And we get the result that we had seen in the other one. Okay, and so we can basically do most of the things we can do in Matlab. We can do them in Simulink. The difference is that in Simulink, it's more of a graphical environment and interaction. And that might be useful to represent some systems. But we already saw that we can do exactly this same thing in Matlab by just using code. Okay. we're going to come back to this because the first lab exercise that you guys are going to do when we come back has to do with the antenna system, and we're going to be working with that. So I'm going to exit Matlab right now because we're going to go back to the original. We're going to go back to the PowerPoints, and we're going to come back to Matlab in a bit. And so let's start talking about block diagrams, because in the end we're talking about representation or modeling of systems. And so now we know that we can create these mathematical models. However, we know that we can also represent them graphically, and that's done using block diagrams, which is something fundamental in control systems. And so how do we represent things with a block diagram? Well, first, the transfer functions are going to be these boxes in the block diagram, or blocks. And what are we going to have here inside the box? We're going to have the transfer function, okay? Inside the box are going to be the transfer functions for the elements that we have in the system. And the arrows that are going in and out are going to be the inputs and the outputs, or the stimuli that we're giving the transfer function and the result we're getting from the transfer function, similar to what we just saw in the block diagram in Simulink. There's going to be another component that is important also. That's called a summing or difference point, which is going to be this circle here. That's usually going to have a cross. Sometimes it has the cross, sometimes it doesn't. That is going to receive signals. Usually in the symbology, there's two signals that are being received. And those two signals, depending on the signs that we have on each, are going to be either added or subtracted. And the result is going to come out here. The result comes out here. And also, when we have a line and then another line comes out, that's a bifurcation. That means that the same signal is being sent to more than one place. So it's important that the boxes are going to be transfer functions. Those are going to be things that we are modeling. Okay, so things that we're modeling. The lines are going to be signals. Okay, that's important. So the lines are going to be signals in our system. Okay. And so this that we have here, which is basically what we saw in the diagram in the example that's already there in Simulink, this is the representation, the general representation of a closed loop system. And let's analyze a little bit what components we have there in this closed loop system representation. By the way, the letters that are being used and the terminology, that's usually a standard control systems terminology that's used. We can actually name them however we want, but usually in control systems theory and books, these are the names that are used. That's how they're tagged. So we're going to use those also. There is going to be, remember that this system in the end represents one major box, which is the system that we're analyzing, whatever system we want to analyze. And so this system that we're analyzing has an input, okay? Is going to have an input. That input is, we're going to call it R of S, okay? I believe the R of S, the R comes because it's the reference, it's the set point, it's the value we're giving the system as an input. In this case, the R of S, this is going to be the desired value. Remember that in a control system, there's going to be a desired value or the objective, and we want the system to behave to get to that desired value. So R of S is going to be the reference or the input to our system. And we're going to have an output to the system. That is the result that is going to occur due to the input that we're providing it. So for example, for the mass spring system, the input, for example, was an impulse, and the output was the sine wave that we got. And so the system is going to have an input and an output. And there's going to be things here inside the system. Now, if we're talking about a closed loop system, well, remember that in a closed loop system, we have feedback. And the feedback isn't anything else than the output of the system being compared to a reference, and that information is used to control the system. And so what we have here is that we have the output of the system, the whole output of the system, and that output is being measured. And the measurement component, which is the feedback component of the system, is usually referred to as H of S. This is the measurement. I chose a long word to write with my arm hurting. Measurement. That represents the feedback. And that is going to have a transfer function. That transfer function is usually represented as H of S. And so that measurement is done, and we get a signal out of that measurement that's called, we're going to call it B of S. And that is going to be provided to a comparison point, which is going to be this comparison point. And basically what's occurring there in the comparison point is that the reference, which is the input, is being compared to the measurement of the output. That comparison is done by a subtraction because that's why it's called negative feedback. So basically, I'm subtracting the reference input from the measurement, and something is coming out of that, which is called the error signal. That's why we refer to it as E of S. This is the error. And the error isn't going to be anything else but the difference that exists between the input reference and the measurement of what's happening of the output. That error system is given to another transfer function, which is going to be G of S. And G of S is called the open loop transfer function. What does this mean? If our system didn't have feedback, that would be the transfer function of the system. So if we didn't provide any sort of feedback to our system, if we didn't measure the output, that would be our system. And that's called the open loop transfer function. And the error is processed, given to the open loop transfer function, and we generate the output. Now, if we were to do a zoom to the open loop transfer function, or the transfer function here in the middle, we would actually see that this is going to be comprised by many blocks, actually. Okay, this is going to be comprised by many blocks that are going to represent the many components of the system. And we already saw that with the azimuth antenna. The forward transfer function had many blocks. The controller, the motor, the gears, etc. So that is actually going to be a sort of a compilation of all of the blocks that are there, and we call that G of S. Okay. Now, let's try to find an expression, a mathematical expression that's going to help us represent this general idea. And so for that, the direct transfer function, or the open loop transfer function, is the relationship between the error and the output, and that's given by G of S. And this is called the open loop transfer function. Now, the complete transfer function is going to be the relationship between C of S and R of S. So let's play around with that to see what we get. Let's try to find a mathematical representation of this with the information we have. Okay, so first of all, E of S, we're just gonna play around here with what we know. E of S is gonna be equal to R of S minus B of S, okay? And why? Because we have a summing point here. So E of S is gonna be the difference between R of S, which is the input, and B of S, which is the signal of the measurement. And B of S is going to be equal to C of S multiplied by H of S, which is the output multiplied by the transfer function of the measurement is equal to the measurement itself. So we've got these two. And we've already defined that the transfer function G of S is a relationship between the output and the error. And from that, we have that C of S is equal to E of S multiplied by G of S. If we play around with these, substituting these two here, and I'm sorry, if we play around with these and substitute them do some, we can say here that E of S is also equal to, I'm sorry, G of S is equal to C of S divided by E of S. This is the one we had already talked about previously. And this one here comes from H of S is equal to B of S divided by C of S. And if we kind of start playing around with these and substitute them into the previous formulas, E of S is equal to R of S minus B of S. We can substitute that one here and we get R of S G of S minus B of S G of S. We already know that B of S is C of S multiplied by H of S. We factor G of S here in this expression here. And remembering that what we're trying to find is the relationship between C of S, which is the output, divided by R of S, that is the input, then we obtain that the transfer function, the complete transfer function for a feedback system is going to be G of S, which is the forward transfer function, multiplied by 1 plus G of S multiplied by H of S. And so this tells us that the only things we need to be able to represent the whole system or the whole transfer function for the feedback system, we only need to know the forward transfer function, which is this one that we have here, and the feedback transfer function. As long as we have those transfer functions, we can represent the whole system using this expression. And this is going to be a very useful expression, a mathematical expression that we're going to be using a lot moving forward. However, there's actually already defined some functions in Matlab that do this. So we won't even need to do this manually. We can we can have this automated somehow using the software. And in the end, the transfer function for the closed loop system is given by this expression that we have here. Now, let's look at the transfer function for the azimuth antenna system. we have all of this, we have all of these boxes there. We've got the amplifier, the power amplifier, the motor and load, the gears, the pot, which is the feedback measurement system, and the pot, which is the input. So that's the transfer function that represented the system that we had, okay? And we want to find the complete transfer function that represents the behavior of the antenna. Why? Because we kind of want to play around with it, okay? We want to play around with the system, and we want to see how the system behaves and be able to work with it and use it in Matlab and in Simulink. And we're actually going to be working with this example. And I'm giving you here in this table some of the values for these constants and parameters that we have here. So we're actually going to be using different configurations. This is one example of configuration for the antenna, where we're given some values, and similar to the exercise we did previously, where we looked at the mass dampener system, and I believe Luis said, well, what happens if we vary the mass and give it different values? What's going to happen? Okay, well, we saw the behavior. Similar here, we're going to see that the antenna behaves a certain way, and depending on the values we give the parameters, we're going to see that the behavior of the antenna changes. But first of all, how could we find the general representation for this whole system? And let's use what we know up to this point. Okay. So we've got the antenna system here. So, and again, please be patient with because I'm not being able to write very, very quickly here. So first off, to find the whole representation or the whole transfer function for this system, we need two things. We need the forward transfer function and the feedback transfer function. And so this box that we have here, this is the feedback transfer function. We only have one box there, so that's it. So this would be H of S. Okay, so I'm going to write that down over here. H of S is equal to, in this case, what does it say there? It's K pot. Now I need G of S. G of S would be the forward transfer function, or the whole transfer function of what's inside the loop. G of S would be this box here. I need this here. I need G of S. I need that. How do I obtain that? Well, we're going to start using and talking about block diagram algebra. Okay, algebra block diagrams, which is actually quite simple. In block diagrams, the algebra of block diagrams is that if I have boxes that are next to each other, so there's one box that feeds into another box that are connected in series. So boxes that are connected in series literally multiply each other. So these four boxes that I have here, to obtain the whole box that represents G of S, the only thing I need to do is to multiply these four transfer functions. So G of S is going to be equal to the multiplication of the transfer functions that we have there. And so these are four functions here. Remember, this material is in Blackboard, so if you need to look at the zoom of the things there, you can see it there in the PowerPoints you have. Pablo, please go ahead before we continue. You have a question. Go ahead, please.
Yeah, it would be just whatever's inside each block, or you see how you have like BP of S, like the output of each block?
Oh, good question. We only take what's inside the block, the box or the block, and that's what we're going to literally multiply.
Okay.
And so, for example, the first thing, and it's literally, remember that the transfer functions have a certain structure. It's numerator and denominator. Transfer functions have a numerator and a denominator. Here in this case, kpot has a denominator of 1. Okay, but it's still numerator and denominator. So basically what we're going to do is multiply all the numerators and all the denominators. And that's literally the way we do the algebra there. So the numerators are going to be k. Then here it's k1. Then we've got k, ka, I believe. Oops. I'm gonna just go back here. It's km, I'm sorry. And kg. And then on the denominator, we have s plus a multiplied by s plus s plus am. That's the denominators being multiplied. But I don't like the way that looks because I don't want this s here in the middle. Just so just to do this in a bit of a more order, I'm going to put the s over here and just do this, which would be equivalent plus am. That would be the forward transfer function, which is the transfer function of the block that's on top. Okay. And what would be the transfer function? And I'm gonna write this down here in yellow, in orange. What would be the transfer function of this part of the system? Okay. And I'm going to call this one, just for lack of a better term, I'm going to call this A of S. Just this box here. It would be the feedback of the system because we've got the forward and the reverse. So A of S would be G of S divided by 1 plus G of S multiplied by H of S. And we're going to do that in a moment. And the whole transfer function for our antenna system, which is going to be the whole transfer function that we need, is missing one component. And I'm going to call this, just for lack of a better term, I'm going to call this T of S. The whole transfer function of the system, which is basically going to be the whole transfer function of the system, which is going to represent the output and the input, is going to be this orange box that we've got here that we've already created, multiplied by this box here, which is the pot box, which would be, I'm gonna call this, just for the purposes here, I'm going to call this box here, which is actually, it's going to be the same as the pot, but I'm just going to call this M. I'm just going to call this M of S. So T of S, which would be the complete transfer function for the whole system, would be equivalent to M of S multiplied by A of S. And we're going to see how that looks in a, we're going to see how that looks in a moment. Okay. Now let me save this screen here. Okay. Now, first off, let's find this one here. Let's find this one here. This is going to be equal to G of S, which is the forward transfer function that we've got here, and it's going to be divided by 1 plus G of S times H of S. So I'm going to write that down here. So G of S is going to be K. Be patient because I'm going to have to write a bit slow here. K1, Km, Kg, divided by S times S plus A and S plus AM. And on the denominator, we're going to have 1 plus G of S times H of S. G of S is this big thing that we've got here, and H of S is K pot. So this is actually going to be K times K1 times Km times Kg times K pot divided by S plus A times S plus A M. And so we've got a big, we seem to have a big mess there, and we need to kind of simplify that a bit, and we're going to do that in a moment. Okay. Okay, we're going to take a 10-minute break, and we'll come back to continue with, we'll come back with and continue with this example. Okay, so 10-minute break. Okay, so this is the transfer function of the orange part here, which is the forward transfer function, the feedback. We've got a box here on the outside that we also have to consider, but right now we're looking here at the orange part, which I'm calling A of S. So we've got this whole mess here. And what we usually do, or what usually happens in these situations, is that we're going to multiply by the denominator. So we're going to multiply by the denominator, which is this and this, which is actually going to be a common denominator that we have there. And so we're going to have that this same transfer function, A of S, is going to be equal to if we multiply by the denominator, we're going to get something like this: K times K1 times Km times Kg divided by S times S plus A times S plus AM plus K times K1 times Km times Kg times K pot. Now that would be the transfer function of the orange part here, which is A of S. However, in the end, we want the whole transfer function. So we've got this box here on the other side, which I'm calling M of S, which is the pot that we have here. So we just mentioned that if we've got two boxes in series, they just multiply. So actually, T of S, which is the complete transfer function for the system, is going to be this transfer function that we just found here. And it's going to be multiplied by the pot, which is M of S, which would be K pot. And that's just actually just going to be added here in the numerator. And so this would be the whole transfer function for the antenna azimuth system. Now, depending on the values I give each of these parameters is how the system is going to behave. And now with that transfer function, I have one function that I can play around with, and I can start analyzing the behavior of the system. Now we had to do some algebraic manipulations here, and we had to do some working around this to get to this whole function. And actually, we can do the same thing. We can do it in a very simple. We can actually do it in a very simple manner if we use tools such as Matlab. And we're going to see how we can do that in a moment. Let me just clean this up here. Okay, and let me save this here. And so we're gonna be able to do exactly the same thing in Matlab, and we're gonna be able to do it much simpler, actually, to play around with the system. Before we move along to that, questions here up to this point with what we did here. We're gonna be doing this with any sort of system that has the different blocks in it. We're gonna, in the end, what we want is to have just one model that represents the whole system. So in the original model that we had for the azimuth antenna, we had 1, 2, 3, 4, 5, 6 boxes that represented the whole, the different elements of the system. They were interconnected. Each of the boxes had a transfer function that represented the behavior of that particular box. What we want now is to have one whole transfer function that represents the behavior of the whole system. And that's what we got there at the end. Okay. Questions with this before we move on? No? Questions?
Nope.
Okay. I'm going to clear these drawings and jump to the next slide. And so this is what we have. And actually, we can do this in Matlab. Okay. We can do this in Matlab, and we're actually going to do this in Matlab. And we're going to do it in Matlab, and we're going to do it in Simulink. Okay. To see how we could do exactly the same thing in Simulink. And let's do some simulations there. I am going to switch over to Matlab, and I'm going to be jumping between screens here. Let me stop the share here for a moment and open up my Matlab again. Okay, here we go. Give me a moment. There we are. Okay, I'm gonna open my Matlab and I'm gonna switch over here. Please, you guys could really help me out here. If you have the PowerPoint open and I'm gonna be switching over, but if you can help me out, maybe telling me some of the parameters and values, that would really make this more efficient and quicker. So I'm sharing here my Matlab screen. And the first thing we're going to do is that, remember that in the PowerPoint over here. So just a question, and please confirm. If I do this, you can see the switching over that I'm doing between Matlab and PowerPoint. Do you see that?
Yes.
Okay,
Yes.
good.
Yes.
Yeah, okay, good. Because it's for the sharing. So we had this where we had the parameters, the block diagram parameters, which are the values that we have for all of these parameters for the antenna system. So we're going to input those into MATLAB first. I'm going to say that K pot equals 0.318. Okay. K doesn't have a value. That's important. Why doesn't K have a value? If you notice, there's a box here in the antenna system, which is this box that we have here, that says preamplifier, and we have a K. This is actually the controller for our system. This is actually the controller. Right now, the controller for our antenna system is a proportional control because it just has a K. Meaning I'm going to be able to change the behavior of the system depending on the values of K that I changed. And basically, what is a K in a transfer function? It's basically an amplifier. So anything that I add into the system that just amplifies a signal, that's a K. But in the future, we're going to substitute that box for a PID or for other types of controllers. Right now, it's a controller. It's what's called a proportional controller because we only have a K. So we're going to be playing around with that value. That's why it doesn't have a value. We're going to leave it blank. For now. Or rather, instead of saying that we're going to leave it blank, we're going to define a value for it right now. I'm going to say that K equals 1. Okay, I'm just going to give it a value of 1 right now. Let me write down the rest of the values. So we've got K1 equals 100. And remember, if you want to be doing this, walking through this as I'm doing this, please do so. And if you have any questions, stop me. So K1 is 100, A is 100, Km is 2.083.
AM is 1.71.
Thank you very much. 1.71.
And KG is 0.1.
Perfect, thank you so much. KG is 0.1. Okay.
Yep.
So those are the parameters that we have in the system. And so now what I'm going to be doing is that I'm going to be defining each of the boxes as transfer functions. So I'm going to have one that I'm going to call syspot. Actually, I'm going to do some copy pasting here. I already have it here in the PowerPoint. Here in the PowerPoint, we've got the different definitions of each of the parameters. I'm actually just going to do some copy pasting there. And so syspot is going to be the definition of syspot is going to be the definition of the pot. I'm just going to remove the comments. So syspot is going to be the the transfer function is going to be just the pot, which is a gain. Notice that MATLAB tells me here on the bottom static gain. What is the pot going to do? The pot is going to receive a rotational value, and it's going to proportionally give me, in this case, it's a pot circuit that's going to give me a voltage that's going to be proportional to that movement. And then I'm going to have the system that defines the preamp. I'm going to remove the commas so we can see them. There. There's going to be one that's called the sys preamp. The sys preamp is going to be the K, which right now is a value of 1. Then we've got the power amplifier. Notice that the systems I'm defining are correspond to each of the boxes of the transfer function. So the power amp is going to be defined as such. Remember that we're using the parameters as they are in the as they've been defined. Then I'm going to be using the sys motor. And Daniel, please go ahead.
Do you have to turn on my camera to ask the question?
No, go ahead.
Okay. So are these these are the transfer functions for each like box, but with like the values already, right?
Yes.
Not
Yes.
the variables.
Yes, correct, Daniel. So they're the transfer functions, but we are defining a specific configuration for values of the parameters right now, and that's this configuration 1 that we have here. Why? Because actually, this is Daniel's question is important. When we're working in Matlab and Simulink, we need the parameters to be able to do the simulation. We can't do a generalized simulation with the parameters as variables. We need values to be able to see a specific situation for the system. So right now, Daniel, the parameters we're using for each of these boxes are the ones that we have defined here in this configuration. Okay?
So you're always going to give us like a table with all the data, like the configurations.
Yeah, we need to know the specific values. So if we're using a sensor, for example, if one of these were the temperature transducer, well, you would need the information to be able to define the model for that specific type of transducer. If we're talking about a motor, there's a transfer function for a motor. The motor and load, this is the transfer function for a motor. But for a specific motor that you're going to be using for the system, there are specific values for these parameters, and you're going to have to input them into the transfer function for that specific case. So you can get those from, if these are theoretical problems, you're going to get them from the problem. If you're doing a real system, where would you get these parameter values? You would get them usually from the specification sheets you would get them from the specification sheets of the component. Okay. And
thanks.
Okay, good. Where was I? Sys gears. And we've got the gears, which was the last one. So now we've defined each of the boxes. We've defined each of the transfer functions in Matlab for each of these boxes. Now what are we going to do? Well, now we're going to use some functions in Matlab that are really practical for this. So one is a function called series. Okay, it's a function called series. What does the series function do? Now let's jump over here to Matlab and do a help series. Basically, what series does as a function is that given a bunch of transfer functions, right now it says M1 and M2. If I have a bunch of transfer functions, it's going to do the multiplication or the series operation or the convolution. So basically what we did previously where we multiplied each of the boxes, the series function in Matlab is going to multiply all the transfer functions I give it. And so I'm going to call this sys azimuth open loop, which is going to be this part here, which is basically G of S, is going to be the multiplication of each of these boxes that we've got here. Okay. And so this function here, open loop, is going to give me the multiplication of this part that we have here. Let's input that into Matlab and see what we get. Let me remove the semicolon so we can see the result. Remember that if we use the semicolon in Matlab, we don't have an echo on the window of what we're seeing. And so we've got that there. And so this is the open loop transfer function, what we have there of the azimuth antenna system. It's a third order transfer function. So what Matlab did is that it did all of the multiplication of each of these. And what we're doing is, since the series function works with pairs, then I'm doing the series of 2, then the result of that is with another component, and then the result of that with another component. So I'm taking them in pairs. Lastly, what we have to do is that this transfer function that we got here, this transfer function that we had here, we are going to do a feedback. There is a function in Matlab that's called feedback, which basically applies the feedback function to an G of S that I'm giving it, and an H of S that I'm giving it also. Okay. Oops. And so the feedback function, which is this one that we have here, is going to take 2 transfer functions, which is the forward transfer function and the feedback transfer function. And it's automatically going to apply this formula that we had already seen here. The feedback function in Matlab is basically going to apply this formula according to the 2 transfer functions I give it. So if I say help feedback, basically given 2 transfer functions, it's going to calculate the feedback, the complete feedback function of that. So what we're going to do is, I'm going to do that in 2 steps actually, just so we can see that. Let me just copy paste this. Give me a moment. Let me just copy paste the first part. So if I apply the feedback, I'm going to get this, which is basically the feedback transfer function. And if I multiply this by the pot, I'm going to get the complete, how do I do that? I do that with the series function. I'm going to get the complete transfer function for the system. Okay. And so this is the complete transfer function for the azimuth antenna system according to the configuration parameters that we gave it. Okay. Basically, in the expression that we had found previously, if we substituted all of the parameters that were given in configuration 1, we would get that expression. Now, why is this expression going to be useful? Because now we can see how the antenna reacts. Okay. Now, I'm just going to run an example here. I'm going to give the antenna a step function for cis azimuth closed loop. I'm going to give it a step function. What does this mean? Let's go back here before we do that. In the azimuth antenna system, what is the input to the system? What is the input that I'm giving it? Or rather, when we say the input, what is the reference, or what is the desired value that I'm giving it? Daniel, go ahead.
The angle.
Perfect. It's the angle. Mm-hmm.
Yeah.
It's the desired angle. That's what I'm giving it. By the way, I didn't mention this, but by default, when we're talking about angle, we're working here in radians. Okay. The conversion of the angle is in degrees. It's in radians. So the input is the desired angle. Okay. Daniel, go ahead, please.
Oh, never mind. I forgot to lower my hand.
Sorry about that. Let me do that. Okay. So
thanks.
The input is the desired angle, and the output is going to be the real angle that the azimuth antenna moves according to the configuration we're giving it here. In this particular configuration, I'm giving it the angle, and right now I have an amplifier of K, a K amplifier, which has a value of 1 right now. If we give it different values, we're going to have different results. So what I'm going to do here is I'm going to give it a step function. Does somebody remember in the step function is a constant. Does somebody remember by default what is the value of that constant? Whenever we use the step function, what is the value by default?
Wasn't it
One.
one?
1, perfecto. Oh, what did I do there? Perfect. It's 1. By default, if I just apply a step function, by default, I'm giving it a 1. So what am I doing here by applying the step function? I'm telling the antenna to move 1 radian. Okay? We're going to see further on what it means if I wanted to go to 30 degrees. Well, I need to do a conversion and do some things there. But by default, when I apply the step, I'm telling it to move 1 unit. And in this case, if the units are radians, I'm telling it to move 1 radian. Let's see what happens when I tell the antenna to move 1 radian according to the this configuration that I gave it. So I just clicked enter there. So what's happening there? Somebody, you are seeing the graph there, yeah. Okay, somebody interpret that graph for me. Again, we have the antenna system. Remember, it's the azimuth antenna that's moving, and we already modeled the whole system with the function that we got, and I gave it a step function telling it to go to 1 radian. Somebody interpret what the antenna is doing.
I think it's moving.
Who's speaking, please? Just so
Jose,
go ahead.
Okay. I think, I don't know why, because it's positive, I think it's going right. And the goal is just 1. It just want to hit 1, and I don't know, with the progression of time. And when it's getting closer, the acceleration is going like, what can I say? Going like less, going
Slower.
Slower?
Yes, slower, yeah, thank you. It's going slower when it's going to hit 1.
Okay, good. That's a good interpretation. Good. Let's see. Give me some more. What that was good, Jose. That was very good. So basically, we're trying to reach 1, and you're noticing that it's trying to do that, and then it's starting a bit fast, and then it's going a bit slower as it reaches it. Good. Anything else that we see there in the graph that can tell us how the antenna is behaving? And remember last class when I asked you a question, what are we interested in looking at here? So tell me that. What do you see here? Adrian, please go ahead.
That is going to last approximately like 100 seconds to do
100
all the
seconds.
process.
Yeah. So we told the antenna to move 1 radian. Somebody do a quick calculation because I'm bad at this. How many degrees is 1 radian? Somebody do that calculation for me, please, because I don't want to do it. Tell us how many degrees is 1 radian.
57.29 degrees.
57.29?
No, 57.29, yeah.
57.29 degrees. So I told the antenna to move 57 degrees. And it's taken, like Adrian was mentioning, it's taking almost 100 seconds. So 100 seconds would be more than 1.5 minutes to reach that destination. To reach 57 degrees, it's taking 1.5 minutes. Okay? Is that clear to everybody? Remember that Matlab can give us some information here with regards to the graph that can be really useful. So let's do that. If we go here to characteristics, let's look at this doesn't have a peak response. Why doesn't this response have a peak response? Can somebody tell me? Pablo, go ahead.
Because like the system goes from 0 to max pretty much, and I'm not sure if it I think it actually gets to there, but the peak is like the end.
Yeah, exactly. It's not going over the desired value. So as you mentioned, there's a maximum value, which is the desired value, which in this case is 1. It's not going over that. So it doesn't have a peak response. So that's correct. It does have a setting time. And so if we click here, and I believe that the setting time here is set for 2%, it's going to take about 66 seconds for the antenna to reach within 2% of the desired value. Okay, 66 seconds. It's taking more than a minute. There's other information here that we hadn't mentioned before, but it's useful. One is called the rise time. What is the rise time? The rise time is another reference as to how quickly the system is reacting, and it's usually the time it takes for the system to react from a certain percentage to another percentage. So it may be usually it's defined as the time it takes the system to go from 10% to 90% of its final value. Okay, so notice here that it's marked here at 0.1 and 0.9. So it's usually how much it takes to go from 10% to 90%. And it's kind of a reference also of the speed of the system reaction. Pablo, go ahead.
Why does the system starts like with a ramp and then it starts with like an exponential? Like right at the beginning.
It looks like that, doesn't it? It kind of looks, that's a good observation, Pablo. It kind of looks like that. I'm going to answer what I think it is. I think that's actually just the graph, how it looks. And that's just kind of the way Matlab is graphing it. We can actually do a zoom if we want. So we can click here and say that we want to zoom here. And so it's kind of having a little curve here, a little jump. That's kind of just the way Matlab is interpreting the step function. But it's actually the curve should be a sort of a clean exponent. Well, no, actually, no, it's not a clean exponential. No, it's not a clean exponential because the transfer function, if you remember, this is a third order transfer function. So this isn't an exponential, a clean exponential. So it's actually doing a curve that we see as concave here in the upwards, and then it's kind of doing the exponential. So that's part of the response. Okay, that's part of the response of the system. Okay.
Oh, okay.
I forgot how to go back. There we go. And so yeah, the system is kind of reacting like this, and then it's doing the exponential. So is it clear that the graph is telling me information about the system? Now, if I modified the value of K, I would get a different response. Okay. And actually, I'm not going to do that now, because that's actually going to lab exercise number 1 is actually you guys playing around with the antenna azimuth system and giving it different values and seeing how it behaves and interpreting. Okay, so that's going to be lab exercise number 1 when we come back. So I'm not going to play around with this now, but you see where we're getting at. Actually, just for the purpose of, I'm actually just going to do one example just for the purpose of you guys seeing how that happens. I'm going to switch over. Questions up to this point before we do a variation? Nope.
No, Professor.
Okay, I'm gonna close this, and I'm gonna do the following. I'm gonna do this a bit quickly. I'm going to define another K. I'm gonna say that K now is, so right now K, which is the parameter we kind of were able to modify, K had a value of 1. And we noticed that the antenna reached its value, its final value, but it took about 66 seconds for that to be the setting time. That might be okay, but what if I want it to be quicker? I'm going to give K a higher value. I'm going to amplify the error signal, and and see what happens there. So now I'm going to say K is equal to, I'm going to say it's going to be equal to 10. And I'm going to do the configurations again. I actually just need to do one configuration again, which is the sys preamp. The others stay exactly the same. I'm just going to do the open loop again and do the closed loop again. And I'm going to run the simulation again also and see what happens. So now what I did is that I increased the gain of the amplifier. Basically what I did is I modified the amplification. I gave it an amplification of 10 now in that amplifier. And the rest of the system stayed the same. Why? Because again, think about the reality. We have a huge antenna and it's behaving a certain way, right? And I want the antenna to behave differently. We already said that if I change the parameters, the antenna behaves differently, right? But let's be realistic. These are the parameters. For example, kg is the gears. Am I going to physically go change the gears of the antenna? No, probably not. Am I physically going to go change the pot that measures things in the antenna? Probably not. That's why I have the controller or something that I can manipulate that's going to modify the transfer function. Now, can somebody please interpret this graph for me? What's the antenna doing here? Pablo, go ahead.
The antenna is like, it's rising, then it overshoots the desired value, and then it's trying to stabilize back to the desired value.
Perfect. So basically, very good, Pablo. So basically, I told the antenna to go to 1 degree. And what's happening? The antenna is trying to go to one radian, which is the 57 degrees. And so it's trying to get to the 57 degrees and it goes past the 57 degrees and then it tries to go back. Okay. And we can see that, we can look at the characteristics. Now we do have a peak response. It overshoots by 0.04. So it overshoots by 4%. Okay. But that might not be a problem, by the way. It might not be a problem for the antenna to overshoot. What did I gain? What was the improvement here in the antenna system? Let's see, Diana.
That it was faster.
Yes, correct. In the previous one, that's very good, Diana. So let's look at the setting time here. The setting time here is 7.31 seconds. How much was the setting time in the previous one? It was around 66 seconds. So in the previous one, where the gain was 1, it took almost a minute for the antenna to get to the 57 degrees. Now it's taking around 7 seconds. Would you consider that to be an improvement in the performance of the antenna system?
Yes.
Could be an improvement. It's faster. Now, the overshoot might be an issue, but it's a 4% overshoot. Maybe the antenna system isn't going to have a problem with that overshoot. The antenna isn't going to break. Okay. Are we okay up to this point? We improved the system, right? So
Yes.
there might be some crazy mechatronics engineers or cybernetic engineers that say, well, let's rock and roll. We've got that the K was equal to 1, and if I increased it to 10, then the system improved. Well, let's give it a higher value. Let's just turn the amplifier up to the largest value, and that's going to improve the system. Well, maybe. Let's see what happens now. Let's now give the K a value of 100. Let's be exaggerated. Let's give it, well, let's do 100. Let's do 100, and we're gonna do the preamp again. we're gonna do the open loop, we're gonna do the closed loop, and we're gonna do the step. Whoa, what's happening there? Somebody interpret that graph. Let me help you out. Let me give you the peak response here. And think about the antenna. Don't just look at the graph. Tell me what the antenna is doing, which is what we should be interested in. I'm helping you out here. I'm actually gonna mark the rise time also. Let's see, Luis, shoot. What do you see there? What's happening?
Well, it's kind of like the one before, but it's trying like much harder to get to the a better settling point.
Mhm.
It's trying to be much faster, but it's overshooting every time it gets around the value.
How much is it overshooting at the maximum there? Luis?
Like 50%.
Okay, so in the previous one, we said it was an improvement because it reached it reached the value at 7 seconds or something like that. That was an improvement, but the overshoot was 4%. How much is the overshoot now? It's 50%. So in the previous one, I told it to go to 57 degrees, and it's probably getting to 58 or 50 or 61 degrees or something like that. Now it's 50% that, so I told it to go to 57 degrees or 1 radian, and now it's going to over close to 80 degrees overshoot. Okay, that's a lot. That's a lot for a peak. Okay, did the setting time improve much? We
No.
gained a second. We gained 1 second there. By the way, Luis, do you have is my class turning into a podcast? You have a very professional setup there. That's
I'm so sorry.
no. This actually looks extremely cool. I want one of those microphones.
Thank you, sir.
Yeah, you're doing your radio program. That's good. So good, Luis, with the interpretation. Yeah, we gained 1 second, but now we're going 50% over what we want. Okay, Marianne, robotics. So let's remember the line follower. Okay. So in the first case, it's following the line, and the deviation we have in the previous case, imagine the line follower, the deviation was 4%. So you're going 4% past what you're moving. So that might be acceptable, okay? Would it be acceptable that suddenly you go 50% off the target and then try to go back? And then what's gonna happen with your car if it's doing that? It's gonna eventually, in practice, what's gonna happen?
It wouldn't find the line again.
Yeah, because the reaction of the components, we're kind of looking at the ideal representation. This is a simulation. You would probably say, yeah, but when it goes 50% off, it's not, my sensors aren't going to be able to react fast enough to be able to find the line again. So this is actually not a desirable result for our antenna system. But again, let's say that we've got our cybernetic and mechatronics engineers that want to go crazy and say, no, but you gave it 100, give it 1,000, and let's see what happens. Let's make the antenna blow up. Why? Because we like to blow up things. Let's just see what the heck happens here with the antenna. Let's be really exaggerated. Let's give it 1,000 gain. Let's do the preamp again. Let's do the open loop again. Let's do the closed loop again, and let's do the step. Let's see what happens now. Whoa, what happened there? Somebody interpret that. What is the antenna doing there? Let me help you out. Peak response. Oops, there we go. Setting time. What happened there when I started to go crazy, Daniel?
Because you're trying to make it like faster, and it's not going like smooth. Like, I mean, it's gonna do with the. I mean, it's overshooting like for like 90% because it's trying to move maybe like because the antenna is so big, it's trying to move like a lot of weight, like super fast. time and the inertia on the velocity. It's maybe like
That's a very good observation, Daniel. I'm glad you said that because you're relating it to the real thing. This is a large antenna, and I'm asking the large antenna to react very, very quickly, and it's got a lot of mass. So it's, if I ask it to move very quickly, or I try to move it very quickly, there's going to be inertia. So I'm asking it to move very quickly, but it's got inertia, and it's going 90% past. And what else do we see there in the graph? There's an oscillation there. There's a very
Yeah.
large oscillation.
we lost like half of it, like double the time from last setting.
The time
Yeah.
doubled. So actually that didn't improve. And we've got a large oscillation for about more than 12 seconds there. By the way, you've got a background there, Daniel. That's a meme, right?
Yeah, I think so.
Oh yeah, because I saw some things in Twitter where there was some screenshots of some students in class that had that on the background. What is that?
Ricardo Naya.
It's Ricardo. Oh, he's in your house and he's going to tell you that control systems classes shouldn't be like this. And he's probably got a taco there. Yeah. I didn't know it was Ricardo Naya because I saw a tweet about a student in a class with that. That's funny. By the way, I never mention names when I do anecdotes, but I had a student fall asleep in class yesterday. It was so funny. I found it funny. I didn't get ticked off or anything like that. The student actually literally was like this. And I couldn't see the student because he was kind of like this and the name in Zoom kind of covered his face like this. And I was asking the student to participate and he didn't react and I couldn't see him. And he was literally asleep with his mouth open. It was so extremely funny. Maybe
he was reacting like the meme like thing. He was just trying to be.
He was really, really asleep. He was. I don't know if he was snoring because his microphone was off, but he was really out of it. I didn't even get mad. It's like I didn't even get mad. We just started shouting at him until he woke up, and it was. I understand. I sometimes fall asleep in my classes, so I didn't mind, but I thought it was real funny. If you're gonna fall asleep in a Zoom class, just turn off your cameras for a moment or log off because it's more embarrassing for you guys than for the group or for the professor. And so going back to this isn't a desirable response. Ideally, we don't want a system, even though the system eventually gets stable, we don't want this sort of response. Again, going back to the car, it's like the car is doing this and then eventually it stops, but it took 15 seconds for it to stop and find the line. That's not something we want. Let's be even more exaggerated. Again, we've got this cybernetic mechatronics engineer that says, let's give it a large value. I'm going to give it a very exaggerated value. The last one was 1,000. Last one was 1,000, right? Let's give it 10,000. Do the preamp, do the open loop, do the closed loop, do the step. Now what's happening there?
It broke.
Yeah, that's extremely correct. This antenna got messed up. First off, it's not reacting. It's not reacting. And this has to do with a certain threshold when we have amplification, where the system is trying to react. It's like kind of trying to wake up somebody that's extremely out of it, and you're trying to react. The system is trying to react, and it's not being able to until it kind of pops and tries to react. And here the oscillation is getting larger. And eventually it's going to get large enough that the system is going to break. So this is an example of an unstable system. Okay, it's the example of an unstable system. Now, right now we did this through trial and error. Okay, actually the first lab exercise that we're going to do is that I'm going to give you certain design criteria. I'm going to tell you the antenna should reach a certain value within 5 seconds, and it shouldn't have an overshoot that's more than 10%. And we're going to first, by trial and error, find an ideal value of K for that. And then we're going to see that there's a way to calculate that with more precision. And Matlab is going to be extremely useful for that. The other thing that we're going to see is that we can actually draw the block diagram in Simulink. Okay. Let me just quickly, before we go, I think I have it here. If not, then I don't. Let me see if I think I have I think I have the antenna system just before we go, so you have a good memory before we go to. Oh, no, I don't think I have the antenna system here. Give me just one moment. No, I don't have the Simulink model here, but we can actually do the Simulink. We can do the Simulink simulations here. We can actually draw the block diagram. We can draw the block diagram as we saw it there. And we can make the system. We can actually draw the system exactly as we're seeing it, and that's a way of representing it. I remember I did have it somewhere. Well, we're going to see it when we come back. So we can actually draw the antenna system, and we can draw it in Matlab in Simulink with each of the components, and we can actually do exactly the same simulations that we did here in Matlab, but we can do it with the actual block diagram of the antenna system. That's going to be extremely that's going to be very practical. Okay,